Good day, we are Group 5 of S11 and we'll be discussing the evolution of graphics. But first, what's a bit? Because before we discuss computer graphics, it's really essential to understand what a bit is. A bit is like a switch, the best way to put it actually. Like a switch, you can turn it on or off. In computer science, we represent on as 1 and off as 0. Inside the machine, that's the only actually two numbers it uses to process and pass information. This is usually why computer scientists use powers of 2. Now, you may think, what can I do with only two options? But imagine having many of these switches. With one bit, you can have two options. Turn this bit on or off. And what if this bit had more friends? With 2 bits, we can have 4 options. 3 bits, 8 options. 4 bits, 16 options, and so on and so forth. Basically, powers of 2. But you may ask, where do bits fit into computer graphics? An image presented on the computer screen consists of pixels. A pixel is like a square. It's not really restricted to one color though, like it's not always black. With more of those pixels, you can actually make it represent something, let's say Mario. But why don't you see any pixels on your gadget screens? That's because they're small enough to not be noticeable to us. Most of our screens nowadays are very high definition, so you don't really see those tiny, tiny pixels. Now, how does a pixel display a color? Surprisingly, this actually consists of math and numbers. Each pixel only really needs three to read 8-bit numbers. One for red, one for green, and one for blue. What does 8-bit mean? It just means that it uses 8 of those switches to store actual numerical values such as 255. Remember that a bit can only be 0 or 1. Having 8 of those switches would allow you to represent more numbers. Now, back to the RGB thing. You can actually set each from 0 to 255 to make any color. But you may think again, how is my screen even animating this video with these pixels? The color data of each image is stored in a frame buffer, which is basically a big block of memory. In the first frame, it gets the color data and stores it in a frame buffer. The screen will display these color data, then in the next frame, it will get the color data again, store it in the frame buffer, and so on and so forth. Just basically getting color data of each frame. Technically, what you're seeing is just a picture. The screen is actually just redrawing each image every single time something moves, creating an illusion that it's moving. The screen redraws every frame very fast, and you actually don't really notice that it's just a still image, one after the other.
Now that we've covered the basics, let's go on to graphics then. So these are during the years 2000s and before that. So how were graphics in low capacity bit systems? So back in the early 1980s, home computers only had around 16K or 16 kilobytes of memory. Some higher end systems would have 32 or 64K of RAM or random access memory. So with these old computers, video chips, which is currently a component of graphics cards today, didn't have its own memory and had to share its memory with the RAM of the CPU or central processing unit. So the typical screen resolution back then was 320 by 200 pixels, the small squares we discussed earlier. So a screen would have about 64,000 pixels. So if you wanted to have two colors in the screen, in this case black or white, you would need 1 bit for each pixel in a screen, since as mentioned earlier, a bit could represent a color for black with 0 and a color for white with 1. So doing the math, you would need to borrow 8 kilobytes, which means 8 bits per 8 byte, 8 bits per byte times 1,000 bytes, which would total 64,000 bits or pixels on the screen of RAM from the CPU in order to represent things on screen in black or white. So the problem arises when you want more colors in your computer during this time. If you wanted 16 colors, you would need 4 bits per color so that a pixel could hold 16 possible combinations of ones and zeros. And this means you would need 32 kilobytes of RAM from the CPU, which would be way beyond the 16 kilobytes your computer would probably have and wouldn't even fit the fancy 32K systems. So the same principles applies the more colors you want to add, with 256 colors needing 64 kilobytes and so on. So it begs the question, how did developers work around these restrictions during these times? So here are common methods that were used back in the day to make graphics work around these hardware restrictions. We have three, namely color cells, NTSC artifact coloring, and CPU-driven graphics. So color cells were the most popular. It basically takes the screen and divides it into smaller cells called color cells, wherein you could change the color of each specific cell. So each cell, typically an 8x8 bit or pixel grid, could only have a set amount of colors. And so the whole screen would only need 9 kilobytes to have different colors compared to an 8 kilobyte monochrome screen. Next was NTSC artifact coloring. Depends on if you have it depended on if you had a monochrome or a color monitor. So color would depend on the position of certain bits and the color bit in a color monitor. Meanwhile, a monochrome monitor would just have ones and zeros to represent black and white. Last but not least, CPU-driven graphics, I guess arguable on the least, since it uses the CPU to draw pictures on a screen. It didn't have a video chip to do these things, so it was time-intensive, and it left no time for the CPU to run game or other types of code. Now we go on to our next portion.
So, in addition to these, the video cards or the graphical processing units or the graphics processing units or GPUs were introduced to offload tasks from the CPU for graphics as early as 1981. The point is, these chips you see in front of you right now are dedicated to calculating display and graphics. This meant that these little like dots you see on this square right now, that is the GPU, are a matrix of cores inside the processor doing all of the calculations and mathematics to show you all the pretty colors and magic and the animations and so on of the games and whatnot. Back then, they had to calculate these things one by one, sequentially. Modern GPUs don't really do that anymore because, well, it's just faster to do it in parallel processing. So this piece of equipment you see right in front of you right now is called the IBM monochrome display adapter. This might as well be the very first GPU in the history of mankind. It was developed by IBM in 1981, and just like the purpose of GPUs, it's a board or like a core or a brain that calculates everything relating to graphics dedicatedly. Unfortunately, as with most GPUs of this time, these GPUs did not have a dedicated VRAM, which meant that they had to share memory with the CPU. This monochrome display adapter supported monochrome graphics by from 80 by 25 characters, which means it can only like show around 80 characters by 25, so that's not very big. That's not a very big resolution. And basically, before the IBM display adapter, there's already things like text-based graphics or character graphics or whatnot. So here's a few examples, like text-based graphics such as like this MS-DOS, like CLI, Turbo C, which is an IDE for like programming, and then like for example text-based graphics like this spinning donut written in C. So what you see in front of you right now is called the Nintendo Famicom RF switch. So this thing, this integrated circuit, this black thing you see on the left isn't exactly the RF switch. This is called the PPU, or the picture processing unit. And the picture processing unit is a specialized chip that focuses on producing picture for the Famicom, which is a gaming console, like everybody's favorite gaming console back in like around the 1980s. So this PPU would process picture specialized for 2D games that are made in the Famicom or the NES. And this machine on the right, called the RF switch, would connect to the Famicom, which would then later connect to the TV via a coaxial cable to the VCR or cable TV, because back then TVs used cable, which used radio frequency signals. So basically, what the PPU, basically what this RF switch does is that the PPU sends the information to the RF, and then the RF just basically shows it to the TV, which is all fine and dandy for the technology at the time. Another thing is that there's also this other console called the Atari 2600 in 1977, and it uses a television interface adapter, which isn't exactly a GPU or a PPU, but it's still a specialized chip that generates sound and picture. And the PPU, technically, it's like a predecessor to the GPU. Now we're inching closer to the year Y2K, and some of these video cards, or rather, well, it's more, video card was the more common term used back then, but rather this is called the Intel 748M or Super, which only had 8 megabytes of memory, and it had VGA support, DirectX 5.0, and had 3.5 million transistors, which is crazy. But basically, this graphics card at the time in 1998 was capable of things like, it's pretty crazy how this little GPU, or rather video card with VGA that's only has 64 bits or 8 bytes, can only really can already like display cool 3D graphics like this from Half-Life in 1998, which is roughly what, 2 decades, almost 3 decades ago. So the final graphics card that we're going to present before the 2000s, well, rather, this graphics card came out in the year 2000. It's called the NVIDIA GeForce 2MX. It had 32 megabytes of memory. Isn't it crazy that back then there's only 64 bits, like 2 years before, 64 bits, and now suddenly they can do 32 megabytes of memory, which is crazy. It's AGP video card. It's now capable of DirectX 7 VGA. It has a die area of 64 millimeters squared. Wow, it's crazy. 32 megabytes of SDR memory. And because it's already in DirectX 7, it's capable of things like this.
Moving on, we now ask, how are graphics nowadays with our incredibly powerful computers? To start, graphics nowadays have evolved from simple 2D images to complex 3D graphics and renders, as seen below. Generally, triangles are used for the polygons that shape objects within a 3D plane. You may wonder, why triangles? This is because triangles are the simplest 3D shape. However, as the polygons tend to be filled in with color, and due to the natures of triangles and the 3D plane in contrast to square pixels, simply filling up all the pixels in a polygon with the same color will result in a rather jaggy render. To fix this problem, a method called anti-aliasing is often used. Here, if only a part of a pixel is in a polygon, the pixel will be colored a lighter shade than if it were completely in the polygon. This gives a much smoother look to objects and is even applied in 2D graphics. This can be displayed here with how, without anti-aliasing, details such as the electrical lines and some of the metal railing on the roof has a bit of a blocky or jagged look as compared to the version with anti-aliasing. Additionally, lighting or shading algorithms were also developed in order to determine how bright or dark each polygon should be colored, as without shading, objects would appear rather flat. All of these, along with having to map textures to each polygon, can be very computationally intensive.
Thankfully, GPUs now have become rather powerful. Transistors, the tiny component in computers that act as the bits explained earlier, have gotten so small that manufacturers could simply put more transistors on a chip to increase computational power. Here we can see 3 GPUs from the left to the right, namely the Intel 740, released in 1998, the GeForce NX 7100GS, released in 2007, and the RTX 3080, released in 2020. The jump in the size of the transistors in these GPUs is quite large, coming from 350 nanometers to 110 to only 8 nanometers. Thanks to this advancement in the semiconductor industry, we can see that the RTX 3080, which is one of the top performing graphics cards right now, packs a whopping 28.3 billion transistors inside it. Furthermore, VRAM has been continuously increasing to accommodate the demand for higher resolutions, as 1080p and 1440p resolutions become the standard for most modern devices. We can see this trend clearly in our previous example as well, with the Intel 740 having only 8 megabytes of VRAM, whilst the NX 7100GS and the RTX 3080 have 256 and 10 gigabytes of VRAM respectively. Also, GPU manufacturers have developed many technologies to lessen the GPU's workload at the cost of some image quality. Notable examples include NVIDIA's Deep Learning Super Sampling, also known as DLSS, and AMD's Fidelity FX Super Resolution, or FSR. These two render images at a lower resolution, which is then upscaled to increase the resolution using a less computationally intensive method compared to simply rendering the image at the desired resolution. For reference, AMD's FSR uses a spatial upscaling algorithm to do the upscaling, whilst NVIDIA's DLSS uses a AI machine learning model to do the upscaling.